Hello, I was asked to look into the complexity of computer applications based on the topology data available in the Dynatrace Application Performance Management tool. In the past, various measurements have been used to estimate application complexity. The most basic measure is lines of code, which uses the number of source code records to estimate maintainability. Function points estimate the amount of business functionality an app provides to users by classifying each of its functional units as simple, average, or complex. Cyclomatic complexity is used to indicate the complexity of a program by measuring the number of linearly independent paths through its source code. The suite of metrics for OO design measures the complexity of an object-oriented program based on its classes and methods. Runtime complexity is used to classify a program's algorithms according to how their runtime grows as input size increases. Space complexity describes how much memory a program uses to process data. Back when these methods of computing complexity were invented, applications were monolithic. In today's microservice architecture, apps are loosely coupled to many fine-grained services. Therefore, some of the old measures do not produce correct estimates anymore. For example, using cyclomatic complexity on a modern app's small main module will make the app appear to be deceptively simplistic because the vast majority of its code is in the services that it calls. So the ask that was made of me to look at app complexity based on service connectivity was a good one. The complexity of a composite object is tied to the relationships between the components that make up the object. So to assess the complexity of an app, we need to know about the services it uses and about how those services are chained together. Higher levels of complexity increase the risk of unintentionally interfering with interactions between services and increases the chance of introducing defects while making code changes. The easiest way to visualize an app and its services is via a network graph like this, and measuring the complexity of a graph has been a mathematical challenge for the past several decades. Algorithmic information theory principally studies complexity measures for objects. A fundamental theory of AIT is Kolmogorov complexity, which is one of those infamous theories that was a great idea, but it's not computable. So several approaches have been developed to approximate it, including the coding theorem method. The Block Decomposition Method extends CTM to measure the complexity of n-dimensional arrays. A graph can be expressed with an adjacency matrix, which is a two-dimensional array. So BDM can be used to measure graph complexity. Let me explain BDM with a very simple example. I'll build a couple of graphs using these 20 nodes. The first node represents an app, and the rest of the nodes are the services that the app uses. These two edges indicate that the app directly calls two services. The service represented by node number 2 then calls two other services, and so on until we have a complete graph of the application. Here's a graph of a different app that also makes use of 19 services. So the question is, which app is more complex? We can use some traditional metrics from graph theory to measure the apps. Both graphs have 22 edges that connect 20 nodes. We can compute the longest path in each graph, and for both apps, the longest path contains 8 edges. Another graph theory measure we can compute finds the node with the highest degree, which is the sum of its inbound and outbound edges. Node number 19 for both apps illustrates that the highest degree for both graphs is 3. So traditional metrics for graph complexity have us at a stalemate. However, when we use the block decomposition method equation to compute complexity scores for each graph, we see that app2 is nearly 250% more complex than app1. To compute a BDM score, we need to convert a directed graph like this into a sparse binary adjacency matrix like this, where the value in row I, column J, equals 1 only if there's an edge from node I to node J. For example, since there's an edge from node 1 to node 2, we turn on the bit in row 1, column 2. My example graphs only have 20 nodes, so their 2D arrays only contain 20 times 20 or 400 values. But some of the real apps that I analyzed had more than 2,500 nodes, so their arrays were massive, containing over 6 million values. Let's pretend this array contains 6 million values, even though it only has 10,000. As its name implies, the block decomposition method decomposes an array into non-overlapping subarrays, and then processes each subarray block. BDM extends the power of the coding theorem method by using a combination of Shannon entropy and algorithmic probability. Here's a high-level overview of BDM. A large array is decomposed into smaller blocks. Pre-computed CTM values are looked up in a reference data set because they are expensive to compute on the fly. Unique blocks are counted and arranged in a data structure with their CTM values, and CTM values are combined using the BDM equation to produce a global estimate of complexity for the entire array. Here's a very high-level view of the Python program that I created to analyze real applications. Dynatrace REST APIs are consumed to get JSON documents for all apps and services that were used within the past 3 days, which is the maximum look-back period. And a topology is created for each app, which contains all of the layers of services that each uses. A graph object is built for each app using its nodes and edges, and traditional metrics are computed for each. Each graph is converted into a 2D array so that a BDM score can be computed for each app. I analyzed over 100 real apps, so I can show a few real examples now. After converting an app into a graph object, I could produce a plot like this one. I used service types from the JSON payloads to color the nodes. Towards the center, you can see the web app displayed as a red diamond. Also in the center is a concentration of web requests for HTTP-based requests and web services for REST and SOAP APIs. The majority of services around the graph's outer border are a large amount of database services, plus mostly more web requests. Dynatrace can monitor both web apps and mobile apps, and here's an example of a real mobile app. You'll notice less nodes here than in the previous web graph, especially less database service nodes. So the question is, which app is more complex? The BDM score in the last column of the table quickly shows that the mobile app is significantly more complex, even though the web app has more nodes. This may lead you to believe that whichever graph has the most edges is the most complex, or the graph that has the node with the highest degree is more complex, or that mobile apps are more complex than web apps. But you cannot make generalizations like these, and that's where BDM comes in handy to determine a form of complexity. We'll look at one last comparison, this time between two real web apps. The majority of the first app services are web requests. The second app has a lot more nodes and edges, especially more database services. But even though the Web 2 app has more edges, the Web 1 app is more complex based on its BDM score. I'll finish up by showing one more benefit of collecting and organizing all of the data from the Dynatrace APIs. This screenshot from the Dynatrace documentation shows how their Smartscape tool enables you to visualize how services are connected. Dynatrace automatically detects all microservices that are part of an application. And this screenshot from their documentation shows that you can view applications too. To Dynatrace, an application is the front-end part that you can access via a browser or a mobile app. Notice that none of the apps are connected to each other in this visualization. This is by design. However, since multiple apps can use the same subset of services, it is possible to investigate app relationships. This is a plot my program generated to visualize 3 real apps. All of the apps use a small amount of services, and I used a circular layout to make it even easier to see each of them. Following the brown, orange, and green lines from the apps, you'll see that all 3 apps eventually make the same HTTP web request. Following the thick black lines, you'll see that then they all call a web service API and then use a service to access the same database. So these 3 apps are related based on some common services that they make use of. I first discovered BDM while reading academic papers like these. Since BDM could be applied to graphs, it sounded really promising to measure the complex network of services that an application makes use of. Unlike methods which consider what's going on inside source code or how much memory or CPU time is being consumed, BDM concentrates on structural complexity of the app's microservice topology. As I saw in my own research, BDM is robust enough to scale to very large 2D arrays by using CTM as a microscope for capturing the information content in very small blocks. In conclusion, I do believe that BDM provides a useful way to compare the complexity of various apps, where excess complexity means that their service layers can become brittle and their code can be difficult to change.